Thank you, Manuel, for your invitation here. This presentation is related to the use of FRP as a seismic retrofit system on RC structures, and the idea is to give you an insight of what we did as University of Naples in last years by using FRP for the retrofit of RC structures, and also to give you an insight of what happened in Italy after the recent earthquakes of L'Aquila and other events. So just to give you an idea of what happened in our country in the last 30 years, we had at least 6 strong earthquakes, devastating earthquakes, starting from 1980 in Irpinia, which is close to Naples, which is my university, up to last very recent earthquakes of L'Aquila in 2009 in the center of Italy, which was a really particular earthquake because it involved a big city with more than 70,000 people. Then we had another earthquake in Emilia in 2012, and this earthquake was a particular earthquake because the damaged buildings were mainly industry, so there was a big issue in terms of business interruption. And then just last month we had another earthquake, again in the central of Italy, and we are now involved in the management of the emergency of this last earthquake. So what happened is obviously that RC buildings showed some vulnerability, and if we take a look to the L'Aquila earthquake, which is the most recent and very important earthquake in Italy, we had the earthquake showed us that obviously existing RC buildings are vulnerable, and especially the most vulnerable part are beam column joints. The reason is because they have been designed without internal syrups since up to 1996. So this is the reason why we can easily find diagonal cracks on the joints. Then other failure have been shown on columns, shear failure on columns, and in several cases we had also the soft story mechanism. Unfortunately, the failure of joints was also observed in the recent earthquake that happened just last month in the center of Italy. So, what happened after the L'Aquila earthquake? The first phase of the emergency phase was to establish the usability of buildings. The Department of Civil Protection was involved in this stage, and in situ inspection were performed on more than 70,000 buildings to assess the usability condition. It was established if the building was usable or not, according to a rating which goes from A up to F. This is the results on all type of construction, and this is the result on RC structures. As you can see, there is 26% of buildings with a rating E, which means severe damage, and 43% with rating B, which means slight damage to structural part, but strong damage to no structural part. And then there is 30% with no damage. As a University of Naples, we was involved in the consortium RELUIS, which is an inter-university consortium which operates in Italy as a competence center of civil protection department. And we were involved in the first phase of the emergency phase after L'Aquila earthquake on the usability survey on school buildings. And also we operate to give a support to design strengthening solution for school buildings. So what we did was to perform several analyses on RC school buildings damaged by L'Aquila earthquake. The result was more or less always the same, and the result was that the RC capacity of these buildings was limited by the joint, so by the premature failure of joints. So then, if we want to give a sequence of failures, if we perform a pushover analysis, we typically found that the second problem was mainly found on columns, shear failure on columns, and then the third problem could be in this sequence the ductility and the deformation capacity of the building. So the idea was that Obviously, the focus of FRP strengthening should be on joints, because just by increasing the shear capacity of a joint, it is possible to increase a lot the seismic capacity of these buildings. So what we did for school buildings, where it was necessary to do something in a very quick time to open again the buildings, was to design FRP strengthening of joints to be sure that this school building can be opened again. We also provide guidelines related to the repair and strengthening works of RC buildings, with a section specifically devoted to the use of FRP systems. And our proposal for RC joints was a strengthening solution as reported here. So with a joint panel strengthening solution made by quadriaxial fibers, anchored with U-wraps at the end of the panel, and these U-wraps can also work to increase the shear capacity of beams, and then to use a confinement of columns in order to be sure that at least in the corner joint, which are the most vulnerable part of the building, it is possible to increase the shear capacity, but also the deformation capacity on columns. Obviously, this strengthening solution was investigated by experimental tests, and then we focus also on the theoretical prediction equation. So I have no time to go into the details of our experimental program. I want just to tell you that we performed several tests on full-scale RC beam column joints in the as-built and FRP retrofit configuration, with a light and strong configuration. The light configuration is just above the joint panel, while the strong one, the joint panel plus the column confinement and the shear strengthening of beams. The results of this experimental program were that FRP were obviously effective and able to increase the strength of the joint panel, and if we use also confinement, we can also change the failure mode from brittle to ductile. Since there was not yet a simple and generalized design formulation for the FRP strengthening design of a joint, what we did, we focused our attention on this target, on this goal. The idea was to find a new formulation, and the problem is, in this case, to find a formulation to define the effective FRP strain in the joint, because there are no indication in our guidelines. The only provision is given by the CNR DT 200, which only suggests to limit the FRP strain to 0.4%. But this is, in some cases, very conservative. In some cases, if we use anchoring system, is unconservative. So what we did was to collect data about the use of FRP to increase the shear joint capacity. We collect the data about the strain on the joint, and so we were able to find an expression experimentally calibrated to find the effective FRP strain when we use FRP to increase the joint shear capacity. The formulation to take into account the contribution of FRP was based on a formulation which provides an FRP contribution to the tensile stresses, which has to be added to the concrete contribution, calculated by using the very known formula by Priestley. And this is what we obtained in terms of comparison between the theoretical prediction and experimental results. A quite good prediction with a mean value of 1.02. And thanks to work of Thanasis, this formulation has also been inserted in a new version of FIB bulletin in the chapter 8. So this formulation will be available for future generation of engineers. So coming back to L'Aquila earthquake, as I told you, there were a lot of buildings severely and heavily and severely damaged by the earthquake. In particular, if we take a look to the RC buildings outside the historical center, There were about 1,700 buildings with a light damage on the structural part, and more than 1,000 buildings with heavy damage and severe damage on structural parts. So the government decided as a policy that it was possible to have a public contribution for repair works, but not only for repair works, but also to increase the seismic capacity of these buildings. So the financial support of the Italian government was not only for repairing, but also for strengthening intervention. In particular, it was decided that for heavy light damaged buildings, it was possible to repair and also to attain a financement to increase the capacity of this building by strengthening solution, by using local strengthening solution. This way, in such a way, it was possible to skip the global analysis and to do this intervention in a very quick time. And the financial support was limited up to 150 euro per square meters. In case of building with severe damage, it was allowed to have a financial contribution for repair works, but also for retrofit intervention. The maximum limit was 400 euro per square meter, up to 600 in very specific cases. But for these buildings, it was mandatory to attain at least 60% of new building standard in terms of safety. So the idea was to increase at least up to 60% the capacity of this building, where the seismic capacity has to be computed as the ratio between the PGA demand and the PGA capacity. So it was also decided that a team made by 3 consortium was involved in the reconstruction process in order to oversee the project related to the funding requests. So the RELUIS consortium was involved in the technical check of the funding requests, and what we did was to check the funding requests of about 20,000 funding requests related to more or less 5,700 buildings. So here in this book we collected all this data, which are also reported in several papers that are now available. And what I want to give you are just some preliminary data about the costs of the reconstruction, both in terms of repair costs and strengthening works. So if we take a look to light damaged buildings, the repair costs were about 184 euro per square meters, while the cost of local strengthening solutions were about 35 euro per square meters, so not so much. And here I have plotted the frequency of the strengthening solution adopted by practitioners, which were engaged by owners in order to deal with the funding requests. And what we can see is that after repair works, what we have is that FRP was really most common, the most common solution, because in 28% of buildings, the practitioners used FRP to increase the capacity of structural members, in particular for joints, columns for shear, columns for confinement, and so on. It is also really interesting to see that in more than 50% of buildings, it was decided to do something to improve the connection between the infill and the RC frame in order to avoid the overtuning of infills, which is very dangerous for the safety, and also which impacts, strongly impacts on the repair costs, because obviously this means that a lot of things have to be repaired. So the strengthening solution involved the use of glass or basalt grids applied at the upper part of the infill frame, connected with the RC structure, by also using some steel spikes. In this way, it was decided to increase the performance of these non-structural members. And this is a picture showing this typical intervention. If we give a look to the heavy damage buildings, just I recall to you that in this case it was necessary to increase the capacity of this building at least up to 60% of new building standards. The repair costs results at more or less 500 euros per square meters, while the seismic strengthening costs were about 300 euro per square meters. This is the wall surface of the building. So if we take a look to the frequency of strengthening intervention, I have to tell you that it is really interesting to say that FRP resulted the most common used strategy, but in several cases FRP was combined with other techniques in order to obtain the best, to optimize the strengthening solution. And also there was also a strong impetus for innovation, because we had more than 15 buildings which were on which base isolation was installed, or steel dampers was also used. So this means that now engineers are ready to use also innovative systems. If we go throughout the use of FRP, obviously in several cases just FRP was used, like in this case. This is just an example. This is the location where FRP was used, and in this case the strengthening solution cost was about 230 euro per square meter. While this is a building where a combined strategy was used, shear walls and RC jacketing to increase stiffness, combined with use of FRP for joints. In this case, this is another very common case. The designer, the practitioner, used a combined strategy based on the use of steel bracing, but obviously in the connection between steel bracing and RC frame, he used also steel or FRP jacketing in order to improve the performance of this connection. So at the end, the result was that the seismic capacity of buildings was strongly increased. In the pre-intervention configuration, the seismic capacity resulted in most of cases lower than 40% of what we have as a target today. Then after the intervention, we have a seismic safety level higher than 60%. It is really interesting to know that to increase at least 1 point percentage of safety, the cost could be estimated about 10 euro per square meters. This is a very interesting data. So, just to some conclusive remarks, the opportunities FRP is now no more an emerging, is clearly demonstrated to be effective to increase the seismic capacity of RC buildings, because it is able to avoid brittle failures and to increase the global deformation capacity of buildings. What we need is to have advanced design tools, is to have a continuous updating of the scientific and technical community, this both for practitioners and offices for quality control. We need sophisticated software, because practitioners should be able to implement this solution in their calculation, and this could strongly improve and strongly give impetus on the use of FRP in a traditional market as construction. What about perspectives? Now we are investigating on a new generation of composite system, or new generation of strengthening solution based on the use of high performance concrete mortar with short steel fibers. This could be a good solution, especially in cases where concrete quality is very poor. And this is just what we are doing in this, what is the research ongoing at our university. What we are doing now is to investigate the effectiveness of these steel reinforced mortars as strengthening solution of joints. What we did was to extract from a real building of L'Aquila, which was demolished just because the concrete quality was very poor. We extracted 2 joints and some columns, and now we are working on the experimental tests on this subassembly in order to investigate on the effectiveness of this mortar as a strengthening solution. The preliminary results are quite good, but obviously we need to perform a lot of other tests in order to validate this technique, and also we need of a proper design formulation to validate this new strengthening solution. Thank you for your attention.